Topic for today is finally a simple one that doesn't change anything that we've been doing very much. The only thing that we're going to change is one of the parameters in our energy balance. So the energy balance that we've been using after we rearrange everything looked like a change in temperature with respect to time, and on the bottom was a sum of moles I Cp I, and we had seen various ways to change that to make it a function of x. And then on the top were two terms. One is Q, and the other one was our enthalpy of reaction. So delta H over RA, or sorry, delta H times RA over stoichiometric coefficient of A times volume. That was our general one. When we had an adiabatic system, which is the one that we were studying yesterday and the day before with our in-class example, the adiabatic systems are the nice ones where we've got Q dot is 0. And in fact, I think all of your homework problems have Q dot equal to 0. If the system is not adiabatic, but the temperature is still changing, there's a couple of different words for a reactor like that. The only style of reactor that we're going to worry about that fits that description is referred to as a jacketed reactor. Jacket as in like you put a coat over it, or a jacket. And then for these systems, the change in Q, well, not the change in Q, is equal to a couple of new terms. So we've got a U, an A, and then a quantity of T minus TA. And the only bit of a weird part, we'll try to describe it here in a moment, is there's a negative sign out front. That gets written a lot of different ways. In fact, sometimes if you look through the examples in your book, I think I have you work one of these examples on one of the upcoming homeworks. You'll see one time they'll write it like this with the negative sign, and then the very next line they'll write it without the negative sign. All they're doing is swapping the order here. I don't know why they choose to do that, but if you reverse that order, then you get rid of the negative sign out front. It seems like an unnecessary complication. That is the general form that we've got. And that's what we're going to look at. In terms of what do we call these particular things, the U, if you've already taken 101B, you already know what U is. If you haven't taken 101B, U is called the overall heat transfer coefficient. Overall heat transfer coefficient. And generally the units on U are going to look something like watt per meter squared per Kelvin. It could be any unit of power, right? It could be BTU per square foot per degree Fahrenheit, something like that. But generally it looks like power per area per degree Kelvin. The A that's here, this is the second A that we're dealing with. You'll generally be able to keep track of which A we're talking about. So the other A we had was the pre-exponential factor in the Arrhenius expression. This A is the more probably common A, which is the surface area available for heat transfer. Surface area for heat transfer. Sometimes I get tired of writing transfer, so I just write exfer. And that's a surface area, right? Got units of something like meters squared. Yeah?
If it's watts per meter squared over Kelvin,
yes.
Does that bring it to the numerator and that would cancel with temperature?
That's what I mean when I write it like that. So watt per meter squared per Kelvin. So if you wanted to write that in like SI notation, this would be watt meter to the minus 2, Kelvin to the minus 1, like that. And then the last one here is this TA. I don't know why they choose subscript A, but it works because nothing else has a subscript A. This is the temperature of the coolant. So that'll have units like, you know, Kelvin or Celsius or whatever it is you're dealing with. It is possible that we do not cool a reaction. If the reaction is exothermic, we will typically refer to this as a coolant. If the reaction is endothermic, we often have to heat things up, and so this is not a coolant. It's something that provides energy. We don't really have an analogous word for something that heats like we do for coolant. We don't have a heatant or a heater or anything like that. It's just coolant that's hotter than your stream. The nice thing is, regardless of whether or not the reaction is exothermic or endothermic, and whether or not you're trying to heat it up or cool it down with Q, you always use that expression. The negative signs of whether or not something is heating or cooling are handled inside there. So that is the form that we use, regardless of what the temperature is on the outside or what that temperature is trying to accomplish on the inside of the reactor. All of this is more or less information that you have to be given. You can be given it in kind of weird ways. The U and the coolant temperature are pretty much just numbers. You have to be given those particular numbers. It's possible that I could give you a geometry of a reactor and you would have to calculate the surface area. There's usually two types of surface area. This doesn't come up a lot. I think you'll have to do it on the project. And even then it'll be slightly different from this because you'll be using a different reactor. But just in general, how do we jacket a reactor? If it's a batch reactor, there's about two different ways that we will typically see these things jacketed. So one, I'm just going to draw them both as liquids because those are a little bit easier for me to draw. So if you have a batch reactor that looks like this, and here's your liquid level, you could insulate everything all the way around it. So something like this, that's supposed to be insulation. So that doesn't allow any energy to go in or out. Presumably you would put a lid on the thing as well so that you don't, you know, evaporate all of your stuff. But at any rate, you could have a insulation all the way around. So this would look kind of like an adiabatic system because presumably there's nothing going across the boundaries. And then you would add a tube that goes into the reactor and kind of coils around a little bit. And you would feed your coolant in through here. So you would have coolant at TA coming in here and coolant at TA coming out here. So it kind of goes in and it loops around and then it comes back out. You can design very clever loops if you want, but that's usually how we would draw something like that. And so what's happening here, the loops that you have here are tubes, right? They're usually copper tubes are pretty nice. Stainless steel tubes are pretty nice. And if we zoom in on one particular section, and we want to see what's happening here. What we would typically have is a section of tubing made out of whatever kind of metal that you happen to have. Inside this tubing, the coolant is flowing. And then on either side of the tubing is your fluid for the reaction. So I just generally draw this as fluid circulating around. These are supposed to be arrows of random fluid directions and coolant going through here. So what we end up having then is a little bit of heat transfer. If it's, for example, a coolant, there is energy being transferred from the hot fluid into the cold stream, and that's coming out of our reactor. How do we get that stuff to stir around in such a way as I've done with the yellow parameters here? Most often, if you ever see a reactor like this, there's a big paddle wheel sticking inside that's just sitting there spinning around. There's plenty of complicated ways that you can try to ensure that everything is uniform inside there, but that's the assumption that's going on in there. So if we want to cool a reactor, this is one way to do it. The surface area that we were referring to, that A parameter is talking about this, right? What's the contact area between that tube as it's coiled around and touching the fluid on the outside? That is what we would call the surface area available for heat transfer. Again, if it were a system like this, I would just have to tell you what that is. I'm not going to make you do the geometry of spirals or something to try to figure out how much surface area is in there. but not at all an uncommon method to cool something. We have one of these over in our undergrad lab. We have a body that has a submersible heater that looks just like that. Yes?
In the diagram, shouldn't the temperature coming out be changing, or is it?
Good question. Not yet, but later. Yeah, so it's a good question. The TA that I have here, I've written it as the same TA, this one and this one. It is usually TA in and TA out, so it is possible for the temperatures to change. We will get to that. Yeah?
Just to understand the drawing, what is the yellow and the green with them? Or like the arrows?
So the yellow over here, this yellow, that's just fluid mixing around in the actual reactor. So in other words, that's where your reaction is occurring. The column of gray in the middle is separate from the two. So that's coolant that's falling through the middle portion here. So that's your coolant. I will try, when we get to the flow reactors, we have a couple of examples of both of these, and I'll bring them in so you can see what a cooling system looks like for a flow reactor. The only one of these that we have over in the lab for a batch reactor doesn't have any temperature control on it, so it just looks like a glass jar, which is all a batch reactor needs to be. That's one way. Another way to do it, if you imagine the same kind of system here, we can put our little stir bar inside there. The other way is how the term jacketed comes about. So the other way is to design a system that goes around the outside of the reactor. Right, like this. And so coolant can come in over here, travel around the outside of the reactor up the other side, and come out over here. So we can have TA coming out over here and TA coming out over here. That's where the term jacket comes from, because it's like you're putting a jacket on the thing. Not that uncommon for a smaller reactor. The bigger the reactor gets, the harder it is for a jacket like that to affect the temperature in the middle of the reactor. So you have to stir the thing really well. You have to put like baffles and stuff inside there to try to keep that temperature constant inside. It's really easy to get what are called hot spots with something like this, where the fluid, no matter how well I mix it, the fluid tends to kind of slow down when it's over here in the corners. So it might be plenty fast elsewhere, especially around the actual mixer, but there can be dead zones in there, and those can get very, very hot. There's a case study, I believe, in your textbook of a batch reactor that blew up because it had a hot spot in it. We will, on paper, we will never blow anything up. It won't happen. So that's another form. The only difference here between this and the other one is that now the surface area we're talking about, let me try and make that a little bit bigger, is this surface area. So wherever the edges of the, that started out pretty good and then it got kind of sloppy. Wherever the edges of the tank are touching the coolant coming around the outside. Yeah?
If there's heat transfer going on between the coolant and the reaction, why is it called adiabatic?
It's not. These are called jacketed reactors. So if Q is not equal to 0, these are jacketed, not adiabatic. That's why I was thinking, do we have a good term for not adiabatic? Sometimes you'll see it non-adiabatic, but what we're referring to is something that both the temperature changes and Q is not 0 is something like this, a jacketed reactor. Yeah?
So I'm recently using jacketed, but I'm using continuum stir, but also it had on literature is it agitated. What is that?
The agitator is that little paddle thing that I've got right there. So it's as simple as, anybody know what a hand drill looks like? You know, you drill something into a wall with it. Imagine that, except it's got a paddle wheel on the end, and you stick it down in there and spin it around, and it does that. That's almost exactly what this is.
And the reason why is because we're using supercritical CO2, and I'm trying to find a vessel that I can model.
Mm-hmm.
Would you recommend a jacketed reactor?
I guess it would depend on what you're trying to do. If you're trying to keep it isothermal or not, it would vary.
It's solid and CO2 better.
Let's talk after class, and we'll see what we can figure out. So the area on this one, about the best I could do for an area, if I wanted to ask you to calculate the area, is something like a cylinder. Right? You could have your mixer down inside the cylinder, and then your jacketed coolant would kind of run around the outside of the cylinder like that. So if I gave you like the geometry of a cylinder, you could calculate the surface area of a cylinder and use that. Again, most of the time I'm going to give you the area, so it's not that big of a problem. The only time that's a problem is when we get to flow reactors, and there we will tell you how to get the area. So these are both ways that we can have a U parameter. The one that we can't do very easily is an actual isothermal reactor. If we want to do an isothermal reactor, and not one like on paper that we're going to solve, but if you actually want to build an isothermal reactor, that's almost always a jacketed reactor, and then you put a controller on it. And so you let the controller adjust something about the coolant in order to keep that temperature constant. Most reactions on their own will not be isothermal unless the volume is either really, really tiny or the conversion is very, very small. Generally, the conversion is very, very small. So that was our artist effort for today. Back to that question about TA coming in versus TA coming out. Typically, we will assume that that is constant. How can we assume that that is constant? There's two ways. So if we want to say that TA is equal to a constant, one reason that temperature could be constant is if whatever coolant you have if this is saturated material. So what do we mean by saturated? So for example, let's say it's not actually a coolant and you're trying to heat something up. You could be taking steam and condensing it. So if I take saturated steam, which is in the vapor phase, and I use it to heat something up, all of that energy will come from taking the steam in the gas phase and moving it to the liquid phase. I could design the reactor in a clever way. For example, if I heat the bottom of it, then when the steam hits the bottom and condenses, it falls right back off and it doesn't produce any, or doesn't provide any more energy. But generally, if whatever that is saturated, we typically will assume that that is constant. Whatever energy there is of slightly heating up or slightly cooling down the new phase is usually pretty minimal compared to the enthalpy of vaporization that got exchanged from one side to the other. And so saturated is a nice state to have if you can get it. The other reason that you can have that this is approximately constant is if the coolant flow is large. So if you just dump an enormous amount of coolant into this thing, any of the energy that enters the coolant from the reactor is pretty tiny, and it doesn't appreciably change the temperature of the coolant. So those are two different ways that we can have the coolant temperature be constant. How would you know whether or not the temperature is constant? You would just be told that the temperature is constant or not in terms of working a homework problem. If TA is not constant, which is a situation that you'll look at least on the project and perhaps on maybe one homework problem. If TA is not constant, then you have to write an energy balance for the coolant. And that's not something that we're going to deal with on a batch reactor, but we will come back to that with a flow reactor. And so this adds yet another differential that has to be added to the set for you to solve, because this will also vary as the reaction proceeds. Not going to happen on a batch reactor, but we will come back to it for a flow reactor. The differential here is not too bad either. If you want a general idea of what that looks like, it's minus whatever Q you had before, divided by the mass flow rate of the coolant, times the heat capacity of the coolant. It's not awful. It is awful depending on the pattern of the flow, which is something that we can make more sense of with a flow reactor and not a batch reactor. But it's not a terrible differential to solve. Typically, we assume that there is no reaction occurring inside our coolant. If there is a reaction in your coolant, you've probably got a pretty serious problem. I don't know why you would have coolant that is also reacting. That's a little weird. And so that's the only change that we've got. So whenever we see the overall energy balance for our particular system, like the reactor itself, the only change is that dt isn't going to have a U up here anymore. It's going to have UA, or sorry, it's not going to have a Q. It's going to have a UA times T minus TA minus all the other stuff, which is exactly the same as before, over all the other stuff in the denominator, which is completely unchanged. So this is what we would get for a jacketed reactor. Again, a jacketed reactor is not an isothermal reactor because there is temperature occurring. So just as a review of the general approach for this, if you haven't started your homework yet, this is what you're going to practice. Usually the general problem-solving approach, in fact, we might as well give this its own page because it's important. So the problem-solving approach, generally for any non-isothermal system, consists primarily of 3 steps. The first step is find all your constants. So evaluate constants. What are some of the constants that we have to come up with? There's lots. So there's any heat capacities that you might need, any of the thetas that we were dealing with, stoichiometric coefficients, you better go find all of those. And then some of the other things that are related to constants, things like delta Cp. And then, of course, if you have a jacketed reactor, you'd be looking for things like U and A, et cetera. Right? All those things that are generally given to you in a problem statement. Occasionally, you will have to go look up a heat capacity. You can use, for example, the kcalc spreadsheet to calculate a heat capacity at a particular temperature. Remember, moving on, those heat capacities are always going to be constant, so we're not too worried about that. And then the second thing that you should do is figure out how to adjust any of these for temperature. So along the way, you would have written something like an enthalpy reference or an equilibrium K reference or something like that. So this sort of a step looks like things like, adjust delta H compared to its reference by doing the delta Cp T minus T ref thing. T minus T ref. It can be the same thing for a rate constant K. Maybe that looks like an Arrhenius expression, A exponential minus EA over RT. Right? Or any of the equilibrium relationships that we've got. Those are all the adjustments for temperature. Once you've got that, then the last part is to actually solve the differentials. And this is almost always going to be a coupled system. Again, the reason it's coupled is because we have 2 things changing at the same time, and one is dependent on the other, and the other one is dependent on the first one. And so this is typically where you dig up MATLAB, because you're going to have to solve, on the one hand, the change in temperature with respect to time, which is generally going to be a function of both conversion and temperature. And then you also have to solve dx with respect to time, and that's going to be some other function of conversion and temperature. Right, that's, you're going to experience that pattern quite a bit on the homework and going forward to the other problems. It's the same solution procedure for all of them. The only thing that changes actually going forward is we get a couple extra parameters because we have flow instead of just a batch system. And then the other change that we'll see next week is we will no longer talk about conversion, at least not as its own differential equation. So if you have multiple reactions, we typically do not write an expression in terms of conversion. We write it in terms of moles or concentration or molar flow rates or something like that. So the number of coupled ODEs that we're going to have to solve is very rapidly going to go up when we have multiple reactions going on, because now we'll have at least one for every single species that's in there. That'll add up pretty quick. So to demonstrate what this tends to look like, if you wanted to solve specifically a jacketed problem, if you still have that little problem from, what is it? I think I gave it out Monday, actually, but we didn't really work on it until Wednesday, and then we solved it yesterday. So if we had that reactor, and it looked like this, and now we want to solve it as if it had a jacket on it, what kind of information could I give you, and what would the solution look like? The only additional information I would have to give you, if you imagine printed on that particular page, would be something like U is equal to a number. So I'm going to use 1500 watt per meter squared Kelvin. A is equal to some other number. Don't confuse the two A's. They will almost never have the same units. You'll just have to use your best judgment to figure out which one I'm talking about. One will always have units of area. The other one generally will not. In fact, I don't think the other one, the Arrhenius one, will ever have units of area on it. Never say never, though. Somebody might come up with one. And then the coolant is some new temperature. So great, now we've got like half a dozen different temperatures to keep track of. All those reference temperatures, which can all be different, the coolant temperature that can be different, and then the initial temperature of the reactor, and then whatever the temperature of the reactor is as a function of time. And so the only difference in the solution that we had from yesterday to today is that yesterday we had, this system was adiabatic, so we had Q is equal to 0. The only thing that we're going to change is in that code, we're going to say Q is equal to minus UA times T minus TA. That's it. But it's going to have pretty big impacts on what's actually happening inside of our reactor and how long things happen to take. It does not, fortunately, change whether or not we can solve the problem or really how long the problem takes to solve. It doesn't take that much longer to solve a jacketed problem because the only thing you're adding to it is the UA times T minus TA. So let's take a quick look at these impacts. Hey, we might get out of here about 10 minutes early today. I like leaving early on a Friday. So here's our code from yesterday. I just kept exactly the same example that we had yesterday. So remember, this one was adiabatic. And so what we've got here is something that goes pretty quickly to steady state. So out around like 200 seconds or so, everything is kind of stopped changing. And so this was for the adiabatic state. Let's add that as a title. Right? Here's our adiabatic one. That's the one that we solved yesterday. If we want to change this to a jacketed reactor, we take exactly the same amount of code that we have, scroll down to wherever you found Q, which was right here, and you have a very easy replacement. You say Q is equal to minus U times A times T minus TA. And that's it. Make sure you define the other stuff. So we have U is 1500, and that was watt per meter squared per Kelvin. And A was, what did I say, 4.5 e to the minus 2, and that was meters squared. TA in this case was 320. Right, that's the only difference between the two. You do want to check as you go along, as always, that your units work out. I happen to give all of these in SI units, so they will work out. We solve this again, put a title on there so we know which one is which. And so here's our jacketed reactor, and here's our adiabatic reactor.